It's a great pleasure to have you all here. We have now a new website that I want all of you here to remember, which is, oh, somebody erased this. Who erased that? So it was bss.mit.edu. So you can access all the speaker list and the videos of the speakers that are agreed to there. So you can always refer to the talks for lectures and else. I want first to remind everybody that might not be familiar of the series. So this is actually a C.C. May Distinguished Seminar Series in the honor of Professor May, who is basically professor in the Civil Environmental Engineering Department in honor of his contributions in mechanics and fluid mechanics. And we have the honor of having him today with us. So he's here in the front couple of rows. So we could give him a round of applause. And this is the closing talk of the term. We had a variety of topics this year, and today is the grand finale in fluid mechanics with Professor Howard Stone. So he asked me to keep it very short, but I will have to mention just a couple of things. So he's actually the Donald Dixon and Elizabeth Dixon Professor in Mechanical and Aerospace Engineering at Princeton University. He had received his PhD in chemical engineering from Caltech in '88, followed by a postdoc at DEMT and the Department of Applied Mathematics and Theoretical Physics at University of Cambridge. And I'll skip the middle, but basically he's the current, I was told in some sense, grandfather of the fluid mechanics in the modern era that we have right now.
I'm that old that you have to call me a grandfather. I think we can stop now.
Everything is relative. And he received, of course, numerous awards and recognition for his contributions, including being the first recipient of the Bachelor Prize in Fluid Dynamics and being pretty much in all the academies except the one of medicine. So that's how short I can make it. And so without further ado, please join me in welcoming Professor Howard Stone.
Okay, well, thank you. It's a pleasure to be here. I will say that I think you've been trying to kill me. I've been talking to people since 7 o'clock this morning, but it's been thrilling. It's really been great, and I think the people at MIT know you have a very special community here, so more power to you. I have a talk today that is going to tell you a few things, but the work that I'm going to tell you about is done by my group. I feel very lucky to have a very special research group, and if there are good ideas here, they came from my group. Okay, so before I start, I want to say thank you to C.C. May. C.C. May is one of the wonderful figures we have in the fluid mechanics and applied math community. If you're aware of his work, it's filled with elegance. You read his papers and you will see that. His work covers many different areas, from small-scale things like mud flows to large-scale problems involving ocean waves. He's the author of at least 2 wonderful, thorough, scholarly books. And if you were paying attention at the introduction, you would have realized we both got our PhDs from Caltech. And C.C. May's PhD advisor is Ted Wu. I took a year-long class from Ted Wu. And if you want also to experience elegance, please read the work of a true gentleman and scholar, Professor Wu. And I think C.C. May would agree probably with all of that. Okay, but even if he doesn't, I'm going on. Okay. So I have a couple slides that's just 1 or 2 remarks I want to make about fluid mechanics and research. And then the themes I'm going to tell you about involve separation, so separating particles from fluids or other things that involve separation. So I have a couple slides about that. And then I'm going to try and tell you how you use chemistry to move particles in fluids. It's a subject called diffusio-phoresis. I'm pretty sure that that most people won't know about this, although there are 1 or 2 outstanding research groups at MIT that probably have specialists in it. But the majority of you probably won't know about this. So I'll show you how you can use chemistry to remove particles from a common porous media, and then I'm going to try to emphasize how we're trying to invent a new method perhaps to clean water or concentrate particles in water using carbon dioxide. At the very end, I have a theme that relates to a beautiful fluid mechanics problem that some of the specialists in the audience know, that's called the Landau-Levitch, Derjaguin-Bretherton problem, to name drop 4 famous people in fluid mechanics. It's been well studied for 50 years, and I'm going to tell you one feature that we've tried to work on recently in the last year, which is, can you use this problem as a new kind of filter? So the 2 common themes in the talk are kind of separating particles from fluids. Okay, if there's time at the end, this is just purely whimsical, but if there's time at the end and you want amusement for a few slides, I will try and mention an oceanography problem that's in your cafe latte. Okay, so here we go. Fluid mechanics and research. I will say that something that I find remarkable about fluid mechanics is the fact that whether or not you're studying geophysical fluid dynamics problems of the atmosphere, oceans, or the inside of the Earth at the scale of the size of the Earth, which is 6 million meters, or whether you're studying flow in small devices, which I understand are very common all over MIT, which is at the scale of microns, arguably the same physical concepts apply to all these problems. So the scale is at least 10 to the 12, if not larger. And a beautiful thing I think about our subject is the same principles, practically the same equations, nonlinear though they may be, apply to all these problems. I've always found that a very enriching thing. Now, I've been at MIT now, 12 hours or something like that. And what I'm reminded of all the time is not only the energy here, but the ideas that go all the way from fundamental science to applications. And you might be aware of this, but most people aren't. Many of us think about the flow of research to applications as a linear model. We think, oh, there's fundamental ideas on one side and applications on the other side, and you might have a view about which you think is better. Donald Stokes, a late professor at Princeton, offered another view of this subject, which I'm going to share with you today. And if you haven't seen it, it's called Pasteur's quadrant. It's the idea that ideas are more complex, and ideas have a richer community of people in them. And that is, the graph you should make isn't a one-dimensional graph, it's a two-dimensional graph. It should have the quest for fundamental understanding on the vertical axis and how useful is the idea on the horizontal axis. Okay, he gives examples of people who fill this quadrant. Obviously, it's not so healthy to be in the lower left. My former students in the audience thought I should put my picture here, but I'm not going to. Okay, so Niels Bohr, he puts in the upper left someone who was fundamental to modern science and thinking about the basic fundamental ideas of our world. He puts Thomas Edison in the lower right, someone who cared about creating things for practical use and wasn't so concerned about how to think about them or how to explain them. And the person, in some sense, who I'll say for many of us could be a hero is Louis Pasteur, someone who did fundamental science but was always thinking about applications. And sometimes he did one, and sometimes in the other, and sometimes he put them together. So Stokes refers to this as Pasteur's quadrant. And you know, when I give talks to young students, I say, you know, this might be the hardest place to be, but it's not a bad goal to have. Okay, so if you hadn't seen that, I thought you might appreciate that. Okay, so now the theme of the talk is about separation. So separations can mean many things. You can try to separate two liquids. If you're into alcoholic beverages, you're worried about distillation. If you're interested in oils for cooking, you have to remove water from them. But there are many other kinds of separations. You can separate gases from liquids. You can separate liquids and solids. All kinds of things where you have to do this. You can have dry systems where you have to separate solids. So there are these wide range of problems, and you can also think about physiological fluids where you have red blood cells, and some people want to separate out the platelets, and other people want to identify the white blood cells. Some people want to identify bacteria from a solution. So there are many things that you can think about separating, and there are probably labs all over MIT that do different variants of this. And if you go to the literature, there are many ways that you can separate. You can use a centrifuge, which operates on density variations. The common way that all of us know is you put things through a filter. You pay a large pressure drop to flow material through a filter. If you're familiar at all with the field, there's a A famous set of processes is called field flow fractionation, or FFF for short, which is a set of principles for trying to set up separations processes. And in modern language, there are a number of groups that are trying to filter without traditional filters or membranes, and they refer to it as membraneless filtration. Shown too small on the right are just examples from the modern literature, the lab-on-a-chip literature, and other kinds of literature where people are trying to create new kinds of separation processes using traditional methods. And a common theme, if you're interested in this field flow fractionation, which I should say goes back to a well-known person in the field named Giddings, and if you're a transport phenomena person, the analysis Giddings gives is almost maps on one-to-one to a famous paper from G.I. Taylor, who's very famous in fluid mechanics. Sorry, Manuel, I had to give a little historical remark. But the idea of field flow fractionation is you flow left to right, and you apply some kind of force transverse to the flow as a separating mechanism, and I'll show you something about that today. So there are a large number of separation processes. I'm not going to claim that we're out-competing any of them. I'm going to show you one that's a little different. Okay, so that's my introduction. So now I'm going to tell you about a problem that is well known to those who know it well and completely unknown to everyone else. Okay, and that is this idea in physical chemistry that involves gradients of chemistry, so I'll say a chemical gradient, and it's going to move a particle. And because it involves a chemical gradient, it involves diffusion. And because it involves moving particles, there's the term phoresis. So in the technical language, they refer to it as diffusio-phoresis. And it's work that's been done by a large number of people in my group. But the person who introduced us to the idea is a wonderful physicist who works for Unilever Research, Patrick Warren, and was the person who encouraged us to work along these lines. Okay. Where I want to start, though, is thinking about ions in water, ions in solution, what you'd call electrolytes in solution. And I just want to point out that this problem is all over our universities. It's just most people only look at one part of it. So the standard problem in biology is you want to separate charged objects from a fluid, and when you do that by applying an electric field, you call it electrophoresis. It applies to any charged object in solution. And I've sketched here the fact that around, if this gray thing was charged, there'd be ions in the solution. But if you go to, well, this is civil engineering. If you have a structural part, cements have lots of charges in them, and you can think about what's the role of the charges. And if you're interested in storing energy or acquiring energy, you might use capacitors or supercapacitors to store a lot of energy. That energy is stored in the present role of ions. And I'm going to show you a flow problem which tries to apply a chemical gradient and remove particles. What these have in common is the underlying physical chemistry is largely the same. And so here we go. Oh yeah, so if you're at MIT, a wonderful place to learn about this is notes online or in person from Martin Bazant. Okay, so this is what you learn in a textbook. You take any surface, you put it in water, it adopts a charge. And so you say I have a surface on a vertical surface on the left, and most things, or many things, when you put them in water, like glass, they adopt a negative charge, which is shown here. If in the solution you have ions, even just ordinary water, H plus and OH minus, or salt water, the ions distribute to the right, and the ions, the so-called counter ions, the plus ions, are found closer to the negative ions, and there's a region in the water where Brownian motion acts where you find a distribution of the oppositely of all the charged ions. So you say, I have a charged surface. You say there's a region where Brownian motion acts on the mobile ions. And then far away, you say, I have as many plus charges as minus charges. The system's electrically neutral. This is the equilibrium picture of the so-called double layer. It is universal. It's in all textbooks. It's the one thing you probably know. And what I'm going to tell you is what happens when you don't have equilibrium. And it's something that most people don't get exposed to. Now, what I mean by this is I'm going to show you an effect in a second where sodium chloride, I don't know a lot of chemistry, but sodium chloride, which is a 1-to-1 electrolyte, and potassium chloride, a 1-to-1 electrolyte, according to traditional electrical double layer theory, are identical. The pictures look the same, what you calculate is the same. I'm going to show you an experiment where the experiments are different. The experimental results are different when you use sodium chloride and potassium chloride. Okay, so now I have to tell you what happens when you're out of equilibrium. Okay, but before I do that, I'm going to say, this is the picture I just showed you, and if you have a particle in the solution, you would draw a sphere and you draw all the ions around it. But it's the same picture. The surface is charged, the counter ions are everywhere. I have to tell you one other thing, and that is when you have charges in solution, you talk about the osmotic strength of a solution. There's a traditional textbook picture people have where they show you a solution placed in a tube. There's pure water, say, on one side, and there's salt water on another side, and they place a membrane in between that allows the water to pass. And when you do that, the water tries to dilute the system on the right, and you talk about the system as having a pressure difference, and the magnitude of the pressure difference is proportional to the concentration. This picture says that if you just buy this qualitatively, then anytime you have a concentration gradient, you also have a pressure gradient. Okay, so this idea is also important in what I'm going to tell you about. All right, so I'm now going to show you an experiment that was published about 10 years ago by a French group, by Lidderic Bouquet, who was a visitor here a number of years ago. He did not discover this effect, but he published a beautiful experiment that should tell you there's something interesting that you have to understand. And the experiment goes like this. I'm going to put particles in a fluid and they're going to move. If they move, you have to tell yourself, what's the force? And you need a force if they're moving at some velocity v. So here's the experiment. You take a microfluidic device. There are 3 copies of it here. In the microfluidic device, you have 3 flow channels. They all have the same salt on the left, and you put colloids in the middle. And the picture down below is what would happen if you take a confocal microscope and scan perpendicular to the flow direction. So beginning in the channel, you see this cross-section, and as you go down the channel, you see the same cross-section. The picture on the left says at the flow speed in the experiment at the left, Brownian motion, even though the particles, I don't have it here, are 1 micron in diameter, Brownian motion does nothing. The flow is so fast that the interface stays sharp. All the colloids stay localized. Is that clear? Okay, now you make one change to this experiment. The flow speed is the same. The buffer is almost the same, except you place a little salt just in the outside channels. You flow this down. The flow goes straight down the channel. There is no complicated flow. The streamlines are basically going straight, but the particles move outward. They move towards the salt. Okay? If you do the same experiment, but you put the salt on the inside, the particle stream collapses towards the middle. So you manipulate the particles only using a gradient of salt. The effect is stronger for sodium chloride than potassium chloride. And so it's tunable by not only the concentration of the salt, but the type of salt. And you can ask yourself, what is the mechanism behind this effect? And that's what I'm going to tell you a little about. And then I'm going to try and manipulate it. My group is trying to manipulate it, as are quite a few other groups around the world. Okay? Is it clear what the effect is now? I need you to try and explain. The reason this is unusual, I think, at least for someone trained in fluid mechanics, there are a few of us in the audience, is most of us don't think about chemistry as doing very much to particle systems. And here you manipulate the particles using chemistry. Okay. So here's the idea. All particles in solution you think about as charged. But there's one difference between salts, and that is the cations and the anions may have different diffusion constants. So it turns out sodium chloride and potassium chloride and the chlorine ion, if you measure their diffusion constants, potassium and chlorine have almost identical diffusion constants. But sodium has a very different diffusion constant. And the consequence of that is when you're out of equilibrium, you cause diffusion processes. And diffusion processes create an electrical potential in the fluid. And if you're in chemical engineering or civil engineering and you've used a book by Bill Dean, this is a kind of thing that's mentioned in a graduate textbook. It's known in the physical chemistry literature that if you have a concentration in solution and a difference of diffusion constants between the cation and the anion, then you generate a potential difference in the fluid. That potential difference is effectively telling you that if you have a concentration gradient, you have a potential gradient. A potential gradient is an electric field. And therefore, this classic equilibrium concept from physical chemistry is telling you that if you have a concentration gradient, you get an electric field inside the fluid, and you're doing electrophoresis on particles. Okay? This is sort of in textbooks, and most people don't know. I'll provide plenty of evidence, or at least some evidence, that most researchers never think about this, and I'll show you what its influence are. So this effect is part of electrophoresis. This is the so-called electrical effect, and it's associated with concentrations. And I should say, just to make clear, that when you analyze this, it involves the log of the concentration. There are a number of theoretical papers. There are very good theoretical papers that model this as, in terms of a concentration gradient. The physical effect is a gradient of the log of the concentration, and that makes some mathematical features happen that you wouldn't have happen in otherwise. Okay, so what does this mean? This means if you're a particle and you're negatively charged and you have a concentration gradient shown by the blue and red here, then the concentration gradient creates a field. The field drives ions. If you're a person that thinks about particles, then there'll be a flow. Don't worry which way it is. There's a flow from one side of the particle to the other side of the particle because there's a concentration gradient, and therefore the particle has to move to take the place of the fluid. You can think about this also as just, it's a charged particle, it sees an electric field, and it moves. It's doing electrophoresis. So in the presence of concentration gradients, particles are going to move. And the feature of this, I thought I had this picture in here, maybe not, is that this is effectively what's going on here. By putting salt on the outside or on the inside, you create a concentration gradient, and that's moving particles relative to the fluid. Okay, so now I get to tell you then another textbook thing. If you ask what's the speed of the particle relative to the fluid part you get by solving the Navier-Stokes equations. How fast do particles move? They move proportional to the gradient of the log of the concentration. And there's a prefactor here that theorists have calculated that tells you effectively the speed for a given concentration gradient. Okay, so what would this look like? If you took salt water and you put it next to fresh water and you had a barrier that separates them, you could ask, well, what happens in a system like this? So if it's sodium chloride, the sodium ion diffuses slower than the chloride ion. So when you remove the barrier, the ions spread out. The chloride ion is trying to diffuse a little faster than the sodium ion. Therefore, you have charge separation. Therefore, you have a local electric field. This is exaggerated. The system is trying to eliminate concentration differences. It does it by creating an electric field. And if you keep track of, there's a little more minus than plus, the diffusion process then creates an electric field. If there are particles in there, they will move. The amazing thing about this phenomena is suppose you took a bath where you put sodium chloride on one side and potassium chloride on the other side of the same concentration. All educated physical chemists would say, isn't the system at equilibrium? There's the same concentration everywhere. They're all one-to-one electrolytes. Except that now when you, going the wrong way. Now when you remove the barrier, the sodium ions, which were on the left, are trying to spread out. The potassium ions on the right are trying to spread out. They diffuse at different rates. The problem on the right generates an internal electric field, and again, you would have, if you have particles, you would have a situation effectively just like the one on the left. So this is just telling you that you have to think now about the underlying diffusion problem if you want any hope of saying what happens to particles in a fluid. Okay, so, oh yeah, I did have this picture in here. So what's this picture telling you? This picture is telling you that you can now choose the type of salt, and you can choose the type of particle, and you can manipulate them. You can engineer the system by engineering chemistry. And there are many groups working on this all around the world. I should say the early work was the great physical chemist that some of you would have heard of, named Derjaguin. And the basis of the idea in chemical engineering was developed by two chemical engineers at Carnegie Mellon in the 1980s. Okay, so here's the work we did. We create a model porous media that has a main channel where flow is easily occurring, and it has a side channel that's closed, so no fluid can go in the side channel, or at least by a continuous flow, and I'll refer to that as the dead-end channel. The concept here was originally introduced by Darrell Velligel, who's a professor at Penn State. Now, what we do is we set up an equilibrium where the same salt is everywhere in the channel, and then we modify the salt in the main channel, including particles. And the best movie I have of it is here, to show you the idea. Here are the side channels. They're all equivalent. There's the same salt everywhere. Then we change the salt in the main channel, and we add particles to the main channel. There'll be two kinds of particles, 1 micron particles and 200 nanometer particles. And when you turn on the flow, the channel is a dead end. So the flow, if you ask what the velocity distribution is, the velocity is 0 in the side channels and right to left in the main channel. And when you, because you now adopt a concentration difference, what you see is you can move particles in to the channel. You're moving particles in simply because you created a concentration gradient. And this also points out a separation, that the particles have two different sizes, and the large particles moved a little faster than the small particles. And the manipulation was via chemistry. So you can quantify this. You can plot how long does it take to fill the side channel as a function of the concentration difference between the inside, which I might call CI, and the outside CO. And if there's no concentration difference, it turns out, a couple hours for the fluid, for the particles to diffuse in, because they're just doing Brownian motion, and you should know at the scale of about 1 millimeter, it takes hours to do things. But with a small concentration difference inside to outside, you can reduce it to tens of minutes. And so you can quantify this effect. And to a first approximation, what you can say is, if I give you a 1 micron sized particle, and I ask you what the diffusion coefficient is of a 1 micron sized particle, you could think of a number. If I give you an ion, does it diffuse faster or slower than a 1 micron sized particle? A small ion, 1 nanometer in size. Diffuses much faster. How much faster? 1,000 times faster. So this phenomena is essentially micron-sized particles chasing the diffusion of 1 nanometer size ions. And the ions diffuse quickly and the particles chase them because of the electric field. There's an osmotic effect, but largely it's usually dominated by an electric field created by the system. And because everything is controlled by the log of a concentration, if you ask, how do the particles distribute themselves? They're running along the channel, but they tend to aggregate, accumulate near the moving front. So you get large concentrations in small front-like regions. This is generic. It doesn't matter what the porous media looks like. If you create a concentration difference, you'll move particles inside whatever your model porous media looks like. So I'll just say, we've done some analysis of these systems in one dimension. We've done some numerical analysis solving the flow equations and the distribution of both ions and particles. I pointed out a slide that shows that there's a size-dependent diffusio-phoretic effect. That's a little hard to think through because traditional thin double layer theory doesn't have any effect of particle size. So you have to account for the fact that there might be a finite size of the double layer relative to the particle. And we've been trying to think about applications where you can ask about separations. Now, I should say, it had already been pointed out 30 years ago that because of this effect, and the particles move because they have a certain charge or a certain zeta potential, you can use experiments like that to measure the zeta potential, or you can separate particles because two identical radius particles that have different surface charges, they will move differently in these fields. So you can separate objects based on their zeta potential. The reason that's interesting, I think, if you're interested in technology, is buying a parameter to measure the zeta potential costs tens of thousands of dollars. Using this experiment, at least if you have a high-speed camera, which might cost some money, and a microscope, you can do it for a few $100s. Okay. All right, so that's my first introduction to this chemically driven separations, this diffusio-phoretic phenomena. Now, I'm in fluid mechanics, so, and I think there are a number of people in the audience in fluid mechanics, so I have to remind you, or at least tell you a story that happened to a naive graduate student who happens to be the speaker when he was beginning graduate school at Caltech. And you recognize that if you're in fluid mechanics, all you learn about might be the Navier-Stokes equations. And so it turns out this naive graduate student was studying late one night in the chemical engineering library at Caltech, which is the next building over from where C.C. May was a graduate student. In walked an older, cynical graduate student. And he says to the naive, hard-working, studying graduate student, he says, "Don't you understand that it's all hopeless?" And the naive student said, "Surely you jest, this is so exciting." Now, I should say this is in the 1980s. The Journal of Fluid Mechanics in the 1980s had about 180 volumes in it. It now has about 600. Anyways, the older graduate student points to the shelf of the library, which was next to the naive graduate student, and says, points to 180 volumes of the Journal of Fluid Mechanics and says, "Don't you realize they're all trying to solve the same equation?" And he walked out. Okay, so I guess, it's your point of view about problem solving, what you choose to think about. All right, anyways. All right, well, that's my one story for the day. Okay. All right, now I just told you about model problems using chemical gradients to move particles in a porous material. So now I'm going to tell you a story that I think applies very generally to porous media. It doesn't matter whether it's soil or your clothes. The words I'm going to use are your clothes because this came from a scientist at Unilever, Patrick Warren. And the question that comes up in any porous media is you have multiple length scales present. The multiple length scales might include places where there are large pore spaces, where it's easy for flow to get in, and there might be places in between close-sitting grains where it's difficult for flow to get in. So in any typical porous media, you will have a hierarchy of length scales and a hierarchy of permeabilities. And in the cleaning side of the world, you can ask, how do you get particles out of the porous media? And if the particles are sitting in the large pore space, you can imagine fluid getting in. And if the particles are sitting in the tight pore space, you can imagine it's very hard for flow to get in. So there's kind of a puzzle in this literature is how do you get particles out of the smallest pore spaces? Okay, and that puzzle, that conundrum, is shown by this picture that if you have flow in a system that has a hierarchy of length scales, at the smallest scale, the flow doesn't penetrate well. And so if there are objects in there, how do they ever get out? In the chemical side of the industry, the physics side of the cleaning industry in any kind of porous system, this apparently is a conundrum that was unsolved. And the proposal we have made is that there is something special about many cleaning processes, and I'm going to also try and show you an analog to an environmental problem. And that is, if all you do is try and estimate how long it takes to diffuse just by Brownian motion, say, I forget what I had, 100 microns, it takes a few hours. If you're in a system like you're washing your clothes, most of us aren't going to wait a few hours for anything to happen. And if you're in other kind of environmental cleaning, this might also be considered a long time scale. But what's special is that when you clean in the clothing part of it, you add soap solution, and then the last part of the process is you rinse with fresh water. So you go from a soap solution, which is chemistry, to a system that adds clean water. And that means there's a chemical difference between two systems. And if you're in the environment, there are going to be places where you contact salt water with fresh water. So there are going to be environmental situations where you create chemical differences. In other words, you start with some chemistry. When you rinse, you're putting it in contact with fresh water. And here's the consequence of that. You might think that cleaning is associated with the fluid motion. So the experiment we did to probe this is I'm going to show you what happens if you take a porous media that's a woven fabric, but again, it should be the same for any kind of porous system. We'll soak it in a soap solution, which means it's full of chemical. And then in one case, we're going to put it in contact with fresh water. And in the other case, we're just going to continue it in contact with a soap solution. In both cases, we stir, we create a fluid motion. And the consequence of this is that the system in contact with fresh water has a chemical gradient, and it's the chemical gradient that drives all the particles out of the porous media. The flow does very, very little. So in any kind of porous media question where you can create chemical gradients, our suggestion is it's the chemical gradient that's going to be the large driving force for fluid motion. And this just drives home the point that these are good things to think about if you're thinking about small-scale problems. Okay, so as evidence that most people don't think about this, I'll just say that there's a problem in oil reservoir mechanics, which is associated with the fact that one way you generate the removal of more oil from an oil reservoir, in some cases, as they know, that you not just do water flooding, you do water flooding with low salinity water, so water that has low salt. My understanding is that this is used in practice in some places. There's very little understanding of how and why it works. As evidence for what you might wish to think about, this is a very nice review article that was published 2 years ago, and I just want to draw your attention to section 6, which is mechanisms of low salinity water flooding. There are 8 different explanations given, but the one I mentioned to you, the idea that if you have a chemical difference, you can create local electric fields and move particles. This diffusio-phoretic mechanism isn't mentioned. The only things that are mentioned are the equilibrium ideas. So that's just evidence that although the review article is wonderful, this kind of concept that I'm trying to share with you, it's just not appreciated by many people. So this was my chance just to preach for the field that if you're out of equilibrium, this is an important effect. Okay. Okay, so what have we tried to do with it? So my group came up with an idea that tries to create a chemical gradient using a soluble gas, and it goes like this. We're going to take water and we're going to put it in contact with CO2. The CO2 dissolves in water, and when it dissolves, there's a set of chemical-like reactions, but the first one is the H2CO3 molecule becomes H+, a small molecule which diffuses fast, and a bigger anion which diffuses slowly. The difference of the diffusion constants is more than a factor of 8. Okay, so it's a fast diffusing cation and a slow diffusing anion. And the consequence of that is that this electrical potential that I mentioned before that was responsible for all the effects I was showing you for salts, which is called the electric potential, it's 4 times bigger for CO2 in water than it is for an ordinary salt. So CO2 in water can provide a big chemical driving force. So if you do an experiment where you take any kind of porous system, so ours is a microfluidic porous system, you have a suspension in the pore space and you have gas on either side. If you have nitrogen gas on either side, nitrogen isn't soluble in water. It doesn't form any ions. And so the particles just undergo Brownian motion, so they bounce around. If you put CO2 on either side, the top and the bottom, and in the middle you have negatively charged particles and positively charged particles on the right, what you should think about is when you put CO2 in water, H+ goes into water, H+ should diffuse in, and negatively charged particles should follow it. And so if you put CO2 in contact with water, and look both near the interface and in bulk, what you'll see is that the particles move away from the interface. They follow the diffusion of a fast-moving cation. And if you do the opposite with an oppositely charged particles, the opposite thing happens. So this is just showing that if you dissolve a gas in water, you can manipulate particles. And now we do the equivalent of what you'd call field flow fractionation. We're going to create a flow left to right. And we're going to use a channel that has a porous wall. And on one side of the wall, we're going to put it in contact with CO2. And on the other side, we're going to put it in contact with the air. So we're going to create a vertical CO2 gradient and a transverse flow of water. And the consequence of this is that you now move particles. You come in with a suspension, and you move particles to one side. So the idea is you could call this concentrating particles if you're interested in concentration, or you could call it cleaning water if your interest is trying to remove things from water. And so we're exploring whether this is something that can be exploited technologically now, where you use a soluble gas as a trigger for this chemically driven separation. Okay, so that's my first full story. I have maybe 10 more minutes, so maybe I'll do this. I have one other second thing we've been doing for the last year, which is another separation problem, but I'm supposed to be doing fluid mechanics, so I'm going to tell you what I think is the most famous fluid mechanics problem, a beautiful problem, and then I'm going to suggest a way that you can use it for an application. So here's the idea. I finished the Diffusio-phoresis, that's over, so forget about Diffusio-phoresis for a second. I'm not going to tell you fluid mechanics, so here's fluid mechanics. You take a plate. Oh, I could do it like this. You take a plate, and you lift it vertically out of a fluid, and if you lift it out of a fluid, you can ask how much fluid sticks to the plate. I'll call that H. Gravity acts down, surface tension is gamma. John Bush was teaching a surface tension class. Did you talk about this problem? Did you do it properly? The fluid has density rho and viscosity mu. The plate moves at a certain speed, and you can ask, what's the thickness of the film? This is associated with the name of Landau and Levitch. If you do the fiber version of the problem, the fiber has a certain radius. You lift the fiber at a certain speed. You can ask, what's the thickness of the film? Did you do this problem? Yeah. Is he telling the truth? He is? Darn. Okay, this is associated with the name of Derjaguin, the same person that introduced this diffusio-phoretic concept. But they're more thin film problems. You can have a bubble in a tube. If a bubble moves in a tube and you tilt your head on the side, you'll see a thin film between the tube wall that is then curved at the scale of the channel. That's associated with the name of Bretherton. And there are other variants of this. The amazing thing about the 5 problems I just mentioned to you is in a certain low speed limit, they all have the same solution. And that is, if you're interested in what the thickness of the film is, you measure the thickness of the film relative to some geometric scale. I'm just going to call it the scale that sets how curved a meniscus is. And that thickness is proportional to the capillary number to the 2/3 power, where the capillary number is viscosity times velocity divided by surface tension. It's a universal result, and it's been well studied since 60 years. So I'm going to try and tell you about an application of it, and I'm going to use this Bretherton problem, the so-called bubble problem, as an example. So when a bubble moves in a tube, there's a certain film thickness. On these slides, I'm now going to call the film thickness B. The scale of the tube is R, and R sets the radius of curvature at the end of the bubble. And if you plot the film thickness versus the radius of the bubble, here's this capillary number to the 2/3 power, and the data are all the stars, so it falls very close to the theory of Landau and of Bretherton, which I'll call the Landau-Levitch problem. There's the capillary to the 2/3. There's a small correction at high speeds, which I think I give on a later slide. And many people have studied this for non-Newtonian fluids, for temperature gradients. There are a variety of problems that people have studied it. And the point I want to make is that the thickness of the film is tied to the speed. And so now what we're going to ask is, can we use this speed-dependent film thickness as a filter for particles? So this is work I've done with my graduate student, Estella Yu, and Sepidakota Porous, who's now at Imperial College in London. And the concept is, if you pull a plate from a fluid, the so-called Landau-Levitch problem, you get a thin film, and you can imagine that if you're a particle and the particle is thinner than the film, it can get into the film, and if the particle is thicker than the film, it can't. And what tunes the thickness of the film is that one variable that you control, which is the speed. And so this concept, which we wrote about with Carlos Koloscu and Jeff Morris, is now going to be the basis for doing size-selective particle sorting, where the size selectivity is set by the film thickness, which is set by the speed. And so we do experiments in a capillary tube. We put everything in a square system that's filled with the same fluid to do index refraction matching. And we follow the motion of the bubble using a camera. And a typical picture looks like this. This is basically the end of the talk. In front is a bidispersed suspension of big particles and small particles. And at the back of the bubble, all you're going to see is small particles. And so you're going to filter the system at a speed you get to choose that's just based on what particle size you need to select. And if you're paying attention, you'll see that the film shape, the bubble shape, is a little unusual, and that's in part because the front of the bubble is free of particles, so it's a no shear condition. The back of the bubble tends to be covered with particles. It's a no slip condition, and that changes the film thickness. So this is basically my story. I just have a couple slides that tell you the dynamics. This is a slide I already told you about. If you plot the film thickness versus the bubble radius, there's a certain functional form that agrees with data. If you now replot this, what happens in this problem where there are particles is that wherever the particles get stuck to the surface, the film thickness is twice as the thickness it is where it's thin. And so we're going to control everything at the front of the bubble by using speed to select the film thickness. And the idea that this works is, in the interest of time, I'll just show this. The simple idea is if particles are smaller than the film, they get into the film. If particles are bigger than the film, they don't get into the film. And so we did the following experiment. We take a suspension of 10 micron-sized particles, and we do a separate experiment with 40 micron-sized particles. We choose a capillary number so that the film thickness is in between. And if you do an experiment with 10 micron-sized particles, then at the back of the bubble, you see the particles. They get into the film, and they get behind the bubble. If you use bigger particles, there are no particles behind the bubble. And therefore, if you then increase the speed so you have a larger capillary number and a larger film thickness, then you can find big particles behind the bubble. You can use the bubble just like you would a filter. It's just that speed is controlling how big the filter is. And it's quantitative, so if you measure the film thickness B relative to the particle size, you can imagine there's a critical scale of 1, and it turns out if the film is thicker, we always see leakage. If the film is thinner, no particles get into the film. And I'll just end with this movie in the interest of time. This is what I just showed you. We've demonstrated that if you take a suspension, you can tune the speed of the bubble to self-select out the smallest particles. This is the movie I showed you that has 10 microns and 40 micron-sized particles. We have not looked at how accurately we can do this. We do have experiments with 10 microns separating from 20 microns, and it's very efficient. So if you keep track, I'll just go here. If you keep track of the efficiency, then if beforehand you had a bidispersed suspension, then after the bubble passes behind the bubble, you only have one size particle. And we did this with 20 micron and 10 micron sized particles. Again, before the bubble passes, the suspension has a bimodal distribution, and effectively after it passes, almost all the particles behind the bubble are the smaller ones. So we've shown this concept of a bubble, this so-called Landau-Levitch-Bretherton problem. We've shown the concept of a speed-dependent filter, and because it's only a bubble moving in a tube, there's not a large pressure drop as you would through an ordinary filter. And how flexible this is with different sized particles, we don't know, but it's something that came out about 2 weeks ago, and so we're hoping to explore it more. And effectively, that's my talk. I've tried to tell you these two different particle separation ideas, this idea of chemistry driving particle motion or diffusio-phoresis, a new idea we had trying to use a soluble gas, and then this last part where I think I might have gone a little too fast, but where we use a classic fluid mechanics problem as a speed-dependent filter. And with that, I'm happy to answer any questions, and if you're really bored, I'll show you a latte, but it's really up to you.
How about the latte?
The talk was so bad that you don't want to ask any questions? Sorry, I went a little too fast at the end. I got a little nervous. Phil.
Going way back to the beginning with your microfluidics, with your picture of spreading plumes and shrinking plumes, if you will.
You mean the experiment from someone else?
No, yours, you showed a cartoon with flow not spreading, with the salt coming down, or the particles coming down.
Yeah.
and you add salt and it
Yeah,
spreads, or you add
yeah.
other kind of salt, it goes the other way.
Yeah, that was so. You
Yes.
mean this one?
Yes. So
Yeah.
my question is, have you ever tried that with a dye in the middle? I want to know if the dye spreads.
The
As-
dye alone.
Well, with the salt added.
Yeah.
with
So people have. Our group has done this, and other people have done it with other kinds of particles. You can ask what kinds of particles work. So there are some measurements with lambda DNA, charged polyelectrolytes.
Yeah, so I'm asking
Yeah.
for a non-ionic dye.
A non-ionic dye. That.
Or pigment, or however you would
Yeah,
like to
so I
express
think I
it.
can answer this
Molecule.
way. If there's an interaction between the molecule and the solvent, then it will move at a rate that's thought to be independent of the size of the object and only controlled by the interaction between the object and the solvent.
So you told me the answer, but you didn't say, did you do the experiment?
Yeah, because I can only tell you what we've done. We've done particles, we've done lambda DNA, we've done some bacteria, but
So the reason I'm asking it that way is,
I'm not sure about the dye one.
the reason I'm asking that way is cations like sodium, of course, drag with them a hydration shell.
Yeah.
So and friction is not an accident in those
Yeah, yeah.
descriptions. So the point is that there is a possibility, if
Yeah.
you want, is as they run in, they're essentially stirring to some extent by diffusing into
Right.
the other part of the system.
So the question, but I guess you're asking, if you had a non-ionic object, let's just say a large enough molecule so it's bigger than the solvent, you're asking, might it also be undergoing this diffusio-phoresis, and at what speed?
Yes.
Yeah, that I don't know, but I think what the theorist would say is if there's an interaction like measured by some potential between the object and the fluid, then you would expect a movement.
I'm hypothesizing
But I don't have
you're
the
right,
experiment.
and there's also possible fluid flow on top of that. But
Oh.
maybe we could stop it there
Oh,
for now.
fair enough.
Let someone else ask a
Okay.
question. Someone else.
Other questions?
Michael.
So for the diffusio-phoresis, you mentioned that there's a potential gradient that forms because of the chemical concentrations. Has anyone tried to measure that potential, like get a multimeter?
Yeah,
stick it
so
in?
in the physical chemistry literature, at least back to the 1960s, if not possibly back to the 1920s, for example, in the oil field industry, I've been told that even Schlumberger was trying to do things like this decades ago. Yeah, it's called the liquid junction potential, and it's a standard physical chemistry measurement. What's not appreciated, I think, by most people who do transport phenomena is, as I've tried to show here, is it's a driving force for moving particles relative to fluid. And the importance is creating the gradient.
Okay.
All right, other questions?
Great, thanks. So for the diffusio-phoresis, do you know if it occurs in nature, perhaps for like odor detection or smelling?
Okay, those were almost two different questions. I wanted to say, well, it has to occur in nature because the experiments
I
that
mean,
I've shown
do animals
have
use it, or-
effectively all the words you use when you describe simple systems. You have chemistry, you have gradients, you have particles. Therefore, how could it not?
Right.
Okay. The second part of your question, though, was what were the two examples?
Like odor detection, for example, crustaceans.
So odor detection in liquids?
Yes.
Aha. So
Or chemosensing.
yeah, that's a great question. Tell me more about odor detection in water.
So crustaceans, so you have this kind of like inverse hairy surface. And crustaceans
I
have
know a
hairy
lot about hairy surfaces, right?
So you have the dead-end channels.
Yeah.
They look like the opposite of a hair, I think. And crustaceans have antennae with hairs
So
that they
I can say
flick.
this. I'm not the most well-read person on this subject, but I talked to a number of people I've read. I have never heard anyone try to make this connection. So if you knew something about it, you should ask. And I think I would just say if there's some kind of object that needs to move for the sensing, then you could ask, is it possible that there's a gradient it has to be probably on the scale of the crustacean for it to matter. And then I think you could ask whether or not there's a gradient, and if it has to move a particle, it is one mechanism. Now the speeds here look big because we're at 100 microns and things are moving at microns per second. That sounds a little small relative to Mr. and Mrs. Crustacean, so not sure. There, of course, you'd have other fluid motion effects, so not obvious to me at a larger scale that it is relevant, but
Yeah, thank you.
I think it's worth thinking about because at least the evidence I'll mention one other one in membrane filtration, which is, I'm sure, studied in classes here at MIT. There's a well-known effect that you put many membranes in water, and ion exchange membranes for decades have been known to have a region near the membrane that is free of particles. And there's decades of articles trying to rationalize the particle-free zone. And until 3 years ago, no one had ever suggested diffusio-phoresis as the mechanism for ion exchange creating this kind of effect in driving particles. And there's now at least 2 or 3 articles, I think mostly from a Dutch group, clearly showing that this well-known phenomena, without an explanation, it's being driven by this diffusio-phoretic mechanism. So I think there are problems where it's worth thinking about.
Thank you.
My question is about the aggregation of the particles. Did you see any aggregation between your particles, and if yes, how it can how it affects the diffusion?
Yeah, so you're thinking maybe like near the end here where I showed this, this concentration effect? That was pretty exciting. I'm not sure what you're thinking about, but you're saying some of these problems where we get a large concentration of particles, and is there any aggregation?
Yes.
Yeah, so in most of the things we've done, there's no permanent aggregation. So if you turn off the flow, then Brownian motion just diffuses everything back away. So we can estimate the concentrations from some light intensity measurements of getting probably, I think we estimated in our paper, close to 50 or 60%. But as far as we can tell, they're not aggregates. There's just a large density of particles. That's what you're wondering about?
Yes, because when we have aggregation, so definitely we have larger particles.
Yep.
So it can affect our
Yeah, so we
diffusion
haven't seen any
across the
permanent
membrane.
aggregates.
Okay.
But that might also depend on the choice of particle. And I should say, a concern of ours in the work we're doing is we've mostly studied model systems. Many real systems have many salts, many other molecules, and how those affect the systems, that's an open question for us.
Okay, because in one of your last slides, you showed the bubble,
Oh,
which
right.
filters the
Right.
larger
Yeah.
particles from the smaller ones.
Yeah.
And if we
Did
have
you like that?
aggregation, how we can detect which one is really big particle or it is an aggregated or...
Yeah, for this, all we've been concerned about here is just trying to show that we can create a filter by size. And I don't think it matters in this problem whether the object is an aggregate or not. The question more is, can you tune it so that you can remove one size relative to another? If the object is an aggregate, I don't think that matters here. But, you know.
Have you looked at how the ionic strength of the solution affects how the first part of your talk?
Ionic strength affects, it sets the concentration. Given the concentration, there's an ionic strength. Most of the work we've done is at relatively low ionic strength. Most of the work in the literature is at relatively low ionic strength. This kind of transport problem has the particle moving at a certain velocity that often people write as UP. It's modeled in all these things as a constant, whatever people have a symbol for it, times the gradient of a log of a concentration. This is MIT, so you know that the gradient of the log of the concentration is 1 over the concentration times the gradient. Many people, in theory, just linearize this. That's dangerous because there's a concentration effect. But it also shows that at larger concentrations, the effect gets smaller. And so it's been suggested that at larger concentrations, you should turn this off. I can say there are a couple recent papers by groups strictly or trying to probe the large concentration limit, and they're always seeing still an effect. And but that is an area where it's more of an open question. But the other interesting question besides ionic strength is because larger concentrations typically lead to smaller speeds. And Phil Geschwind mentioned this to me today. If you change pH, pH is known to affect surface charge, and surface charge affects this parameter. So if you have gradients of pH, you can expect more complicated effects. It's something that I've been told about when I've given talks. We haven't studied it. We think we should be studying it, but we haven't yet. But that's also an interesting physical chemistry question.
I guess I'll ask a quick question. So the other term that's in front of here is the mismatch in the diffusion coefficients.
Yeah, that's in here.
Yeah,
That's one of two terms in here. In this parameter that I've written here as gamma p, there's an electrophoretic contribution, which is proportional to the difference of diffusion constants cation to anion. And there's another term that's called the senior moment, the osmotic contribution. The way to think about the osmotic contribution is if you're an object and you like the solvent, you always move to the higher concentration side. The diffusion constant difference can go either sign, so it can flip. It can go either way.
So what I was going to ask was, you point out the difference between potassium and sodium, but has anyone tried to optimize that? Because I'd preferentially choose something like lithium bromide, a really big ion and a really small ion. Lithium has a really high diffusion coefficient.
So the order would be sodium is less than potassium is less than sodium is less than lithium. People have studied some of this. Mostly what people have done are 1-to-1 electrolytes. There's less been done with either 1-to-2 or 1-to-3 electrolytes, but some of this has been studied in model systems. Yeah.
So back to your Nature Communications paper from 2017. So what sets the width scale of the water filtration, and how do you adjust your channel width?
So that's what we are working on. So we are now trying to see if we can optimize the choice of parameters to do this effectively. So if you're a transport person, you need to ask, what's the growth of a boundary layer where you have a diffusing species in a flow? That's kind of a known transport problem. So we're doing experiments and modeling to try to ask what's the optimum length for a given flow rate and a given channel size. So that's kind of ongoing work right now. But it's the right question to ask, or it's one we'd like to answer. And we have kind of preliminary models that are, if you're in chemical engineering or you've studied these problems, you sort of can see how to do. And we're trying to do experiments with different sized particles to test it as a design rule for choosing the length of a channel for a given flow rate. And the only way this will work in practice, we think, is you always have to stay below the laminar to turbulent flow transition, because you need a laminar flow for this idea to work. So that places an upper bound on speed for a given channel size.
Maybe one last in this corner. The microphone is on this side. All right. Here we go.
Thank you. So is there going to be a limitation of the size of your the system that you can apply this to? So presumably, if your system gets really big, you're saying here, your ions
for
can't
this
diffuse
picture,
too far apart.
For this picture?
Yeah, or this diffuse the system in general.
Well, at least in this picture, there is a size issue. There are probably several size issues. This is related to the last question. If I give you a channel size and you give me a flow speed that's so fast that you don't have a laminar flow but you trigger a turbulent flow, then you won't separate. You'll just remix.
But for example, if you take it out of a microfluidic channel and you put it in a pipe,
right?
Is it,
yeah. So the question is size. So if you have flow in a pipe, there's a Reynolds number. Yeah. So you need the Reynolds number to be low enough to guarantee for your geometry that you maintain a laminar flow, both at the inlet and the exit.
Yeah.
And that's a Reynolds number criteria, which involves speed and size. And so from our point of view, you have to stay below there, and then you also have to choose the parameters such that this, whatever this diffusion distance is shorter than the distance you have for the length of pipe you have, and that also brings in diffusion constant and speed. So there are design considerations that we're trying to work on now to select design parameters so that we can do this in practice.
Okay, but so your electric field, to maintain a constant electric field, it means that at longer scale you will have higher concentrational difference between your ions. And
Yeah,
that sounds harder to achieve at a larger system.
Yeah, I want to be careful. The electric field here that I referred to is one that's created by a concentration gradient of ions. There's no applied field.
Yeah.
And that field is maintained by a concentration difference.
Yeah.
That concentration difference is easier to maintain at a small scale than a large scale. Yeah, so all your words then are true.
Okay, so there might be a limitation of the scale eventually.
Oh, I'm sure there are limitations of scale.
Do you know roughly how large it's going to be?
No, that's something we're working on now. No. We're trying to offer a design so that we can ask, what would it take to create a design to scale this system up?
Thank you.
All right. So, thank you very much.